Well, good afternoon, everybody. Thank you for joining us. I'm Dana MILOAGA. I'm a research scientist at Jones Manville and a product leader for the company's new thermoplastic composites team. It's my pleasure to introduce you today my co-presenter and our partner from Forward Engineering, Mr. Georg Kassmeyer. Today we will be talking to you about new exciting organosheet materials developed by Jones Manville through an innovative technology, and we will describe how we advance these new materials through collaborations. If you don't know Jones Manville, first of all, we are present here. We're in booth D84 here in Hall 6. We are an old, 164-year-old American-based manufacturing company. We have 45 plants across the world and over 8,000 employees developing new materials and working in 3 business units. These are installation systems, roofing systems, and engineered products. The first 2 business units are mainly addressing building materials and construction industries, and the engineered products is where we are actually developing materials for the composites industry. The company has been consistently delivering over $3 billion in sales in the last years, and I'm proud to say that we are located and headquartered in Denver, Colorado. So for the composites industry, Jones Manville is offering an interesting portfolio of glass fiber reinforcement. So we are offering everything from direct dry chop strands to rovings, single-end and multi-end rovings. And what's new today is that we are moving into offering thermoplastic composites. So we are shifting from being a supplier of reinforcement to being a supplier of composites as well. So we're branding this under the new name of Neomera that was launched last fall at CAMAX. And under this umbrella, we're starting with continuous fiber reinforced thermoplastics. So we're starting to offer thermoplastic composites as organosheets. And the idea here is to really bring affordable continuous fiber thermoplastic composites to more global markets. The drivers, as you might expect, are in the area of mobility. So we're looking at lightweighting, functional integration, and all the needs that are described in this space and in transportation in general. So what happened is that our fibers team for a long time has been indicating that there is a shift in the industry from demanding short fibers for non-structural applications to an increased demand for long fibers for LFT, so materials that go into semi-structural parts, to really what we're seeing today, a demand for continuous fibers. And those are materials that go into structural applications and really have the opportunity to deliver new benefits, new mass and cost savings to a larger range of applications. The drivers here are, as I said, mass saving, cost saving, and performance, nevertheless. Of course, we are talking about thermoplastics, so those are recyclable materials. What's interesting is that under continuous fibers, we see in the space of thermoplastics, tapes and organosheets, and that's where we'll be focusing on. So in this space, there are already applications that you are probably familiar with. We have seen brake pedals from the Volkswagen Group. We have seen the Valeo bolster developed for Daimler. Actually, that was a finalist for JC in 2020, and I think they even have it at their booth. We have seen some underbody shields. The one that you see there is for a Bentley. We choose that one because it's based on polyamide 6 composites. We saw door panels that Ford is putting in Ford Focus at about, I think, 1 million pieces a year. So there are applications where organosheets have penetrated the market, but there are not that many. So we're wondering, what are some of the barriers that prevent the adoption of these materials on larger scale? And what our technical team in Colorado has done is really they had a closer look at the barriers. And being a glass fiber company, they really understand the glass fiber interface, they understand how composites are made, And what they really saw is that unidirectional tapes and organosheets, which are the two main types of continuous fiber thermoplastics on the market today, share the common manufacturing process and somehow the common limitations, because these two materials are made conventionally by melt impregnation. So people take either rovings or glass fiber fabrics or carbon fiber fabrics and then take a polymer melt and impregnate the array of fibers. The idea is that the limitation here is from the fact that the thermoplastic polymer melt is highly viscous. So for people familiar with epoxies, we are looking at a couple of order of magnitudes difference in viscosity. So it's very hard to take a viscous polymer and then impregnate it into a fabric when you're trying to achieve a thick structure, a thick part required. So on the other hand, the team in Colorado has taken advantage of a technology that was already there. It comes from the RTM. So I'm talking here about the anionic polymerization of caprolactam. So what they did is, for polyamide 6 organosheets and composites, they really took a step further, and then they looked at how we can polymerize caprolactam in situ in the fabrics in a continuous process. So that's a novelty. That's what JM is doing differently, and I think that's what will take us to the next level. So what we're doing is starting with fiber reinforcement in the form of rolls or even chopped fibers. We're taking the caprolactam, the monomer, the precursor for PA6, which is very low viscosity. We are coating the fabrics or the fibers, and then we are allowing this to polymerize in situ, in place, in a continuous process. So continuous is an important word here because this is what makes the process cost effective. So we start with rolls, we start with put caprolactam on, and then at the end we generate thermoplastic composites organosheets. So this is a proprietary process, is continuous, and it helps us, what I said earlier, bring composites to different markets and make them more affordable and more accessible. The technology has been demonstrated for chopped fibers as well. The advantages and the benefits here are coming from the elements that form the composites. So there are advantages from the fibers. You know, there's variety. The technology works for glass, for carbon, for aramid, for combinations of those. You can build some isotropy in the fabric and then, generate composites that respond to a certain need. There are advantages that come from the PA6 matrix also because it's produced in situ, high molecular weight, it's recyclable. There are advantages at the interface. We are a glass company, so we know how to design the sizing that allows for an improved and optimized interface. And also there are advantages from the sheets themselves because unlike a thermoset prepreg, they are easy to handle, they don't have any storage requirements, special storage requirements, and they're really very easy to use in conventional automated processing. So people can use them in a similar way that they use metal sheets. Nevertheless, from a sustainability point of view, we are looking at delivering zero waste. So we're looking at repurposing what we cut out and delivers net-shaped blanks if the customers need. So we're looking at the entire process. And based on that, we are building now a full portfolio of organosheets in which, for the beginning, the resin is polyamide 6, and the fibers can be woven, can be non-creamed, chopped. So depending on the attributes that are needed for an application, people can choose a non-creamed fabric organosheet or a continuous woven organosheet or even a chopped roving if formability is more important. So we're building all of that. We are looking at hybrid options as well and really focusing on tailored and load-appropriate layups so that we can deliver function-focused material selection options. Now, what are we doing with these materials? Like everybody else today, like a lot of people today, we are looking at what are the markets that can benefit for all the advantages and that these materials can bring to market. And one of those markets is the battery enclosure. So we know about that. We know it's growing at a rate that can, after some sources, is about 25% in the next 10 years. So we know that in this space, the steel battery enclosures, were very heavy. We're looking at the Nissan Leaf from 2005. And then we're following a weight decrease in time, right? When people started to use aluminum and different types of aluminum, and then progressively they started to use more composites. So the weight saving is really important. And then we think that we can even bring more through our structural composites. But we can't do that alone. So as a material supplier, you have an exciting new material, but in order to push that, you have to have more. You have to have a solution. You have to have a way to show your customers the path to that solution, and you have to show them that's possible, and then what needs to come into that picture to deliver a good result. So this is why, having the whole image in mind of cost saving, mass saving, and looking at solutions, we decided to partner with others in the value chain. And one important partner that I'm introducing today is Forward Engineering. They really helped us leverage our advantages and build on that so that we can describe what's possible with Organosheets. So I'll hand it on to Georg, who will talk about an exciting concept that we developed together in the last maybe 3 years ago? Yeah.
All right, thank you, Dana. So yeah, as you said, 3 years ago when Dana came to Forward Engineering and told us about this new innovative process to drive down the cost of organosheets with glass fiber, she directly got our interest. Because as Forward Engineering, we see our role as an enabler for new materials, especially for new composite materials for future mobility. We always try to balance the triangle of manufacturing-based engineering with advanced materials and leading to a sustainable product design. And our role as engineering service provider is especially in pre-development projects to accelerate projects and to put them in the right track. So this was actually the recipe we are used to work in. And so we started to think about how can we, at least at the beginning of a concept development process, find the right solution to demonstrate on the one side the advantages of this organosheet, but also on the other side to show that you can really create structures, primary structures with organosheets, because all the organosheets applications we've seen in the market so far were mainly secondary structures. And our role as Forward Engineering is to team up then with the right technology providers and develop the concepts, to do cost calculation, to do also life cycle analysis, and to make sure that these concepts have the best possibility to get into mass production and then hand over more and more throughout the process. So especially when it comes to battery enclosures, we have a range of different requirements. On the left side, you see the mechanical requirements, starting with stiffness. Stiffness is equivalent to lightweighting. That's, I think, where composites come from. But when it comes to battery enclosures, it's much more about lightweighting. It's about fatigue. It's about mechanical shock. It's about impact. It's about durability. We also have to deal with all kind of crash load cases, with impact load cases from the bottom, for example. But it's not only about the mechanical load cases. On the other side, you see also a lot of functional requirements a battery enclosure has to fulfill. One of the most prominent one, and certainly you find many good materials and examples here on this show, how to deal with thermal runaway propagation, but also how to deal with thermal management of a battery enclosure. And we know glass fibers are a great insulator, but does this contribute to the system or not? There were a lot of uncertainties a few years ago. Today, I think the industry knows much more about this system requirements and how to answer it and how to address it. But also when it comes to assembly of battery enclosure, topics like sealing, moisture, but also how does it interact with the overall vehicle and with the environment, especially in the topic of EMI shielding, was very critical. And all of these requirements were the starting point of our white sheet of paper process. And we wanted to show that the Toolbox Jones Manville has developed can very uniquely address all of these requirements. Before we get into the details, I first want to show you the result. As we started on a white sheet of paper, we wanted to make sure that we are on track and that we have a good benchmark. In this case, we started with an aluminum battery enclosure and with a typical weight of 100 to 120 kilograms, but with more than 30 parts. And we calculated a production cost of between $950 and $1,200 per battery enclosure. With this new concept which was developed, we could show that the functional integration and the possibility to reduce the number of parts in these mechanical structures really also lead to a nice design. In this case, with only 11 parts, we can build the primary structure of the complete battery enclosure. And the weight with the glass fiber organosheets is almost on the same level like the aluminum and with almost the same cost. So we see that with glass fibers and with this especially new in situ polymerized organosheets, we can tackle aluminum and steel in various applications. And the battery enclosure is just one of them. But the Toolbox from Manville allows even more. So there were some carbon fiber UD tapes in it. And we said, okay, let's think about it. How could this material contribute to the design? So at least it's like an option to reduce weight if weight is critical to a project. Of course, as we know, carbon fiber is expensive material and it comes along with also some additional cost. But we wanted to show that there is flexibility in the engineer's toolbox. That's what it's all about. The starting point for the design was to have a clear understanding of the stress landscape of a battery enclosure. And here you see different areas. The bottom tray, for example, is more for impact, but also contributes to the stiffness, of course. The outer side, especially on the side sill area, has to deal with the side crash, pole impact, for example, but also rear and front crash somehow are in that area. One big challenge is the local connection points from the very heavy battery packs inside the battery enclosure. So the cell modules, they have a lot of weight. They do a lot of things when they get into dynamic movement. And you can think about what does it mean for the joining technique. So a lot of highly loaded areas we had to get under control. But also the connection to the vehicle. There's also a lot of local spots. And from multiple concepts and possible segmentations of battery enclosure, we really tried to find a very simplified version. And in this case, we built two large parts. The top cover, this is the light blue part, and the bottom plate, the dark blue part. And with these only two very large parts, we have already pretty much of the enclosure. And the benefit is we have only one sealing plane between two parts. So no joining techniques or no little holes or welding lines or anything which makes maybe a problem in the sealing strategy. So very simplified basic concept. But of course the two shells are not rigid enough to do all the mechanical jobs. So we had additional elements like beams. They were thermoformed and hybrid overmolded. And this is now where comes the injection molding compounds into the game. And also thanks to our partners from Lehman & Voss, we found great compounds which contribute perfectly to the mechanical loads of this battery enclosure. So you see the elements, the beams, they get mounted to the top cover and then they build a rigid top enclosure. And in the next slide you see a little bit more about the assembly sequence. So the bottom plate gets assembled with cooling plates but also with the battery modules, and then the pre-assembled and pre-welded top cover gets mounted to the bottom section. And here we use another advantage of thermoplastics. As you know, you can weld them in theory, but also in practical. So also in terms of recyclability and sustainability, the less materials you have in your final product, the better. So without the need of adhesive, we could again simplify the design. And the simple solutions, they are the good ones, and they are the most challenging ones. But we've seen with these materials and the flexibility of combining injection molding, metal inserts, but also organosheets with all kind of fibers, we have a great toolbox as engineers. Of course, we started some also structural simulation to make sure that the dimensioning is right and that we really can tackle aluminum and steel in such an application with composites. On the left side, you see the side pole crash simulation, similar to, equivalent to 100 kilonewton load case. On the right side, you see the stiffness and stress map, which shows that it's a very nice balanced design. So the material really acts as a system, and this is always a good indication for a lightweight design. But beside the mechanical dimensioning and the mechanical design, we also had to deal with the additional functions, as I mentioned earlier. So the good thing is you can add very easily EMI shielding, for example, with aluminum foils, but also with other technologies. Even on the injection molding compounds, you can use additives and make them better for shielding effect, for example. But also you can add thermal runaway protection materials, and we've seen the combination of this fire resistance materials and the glass fiber offers an outstanding performance in comparison to aluminum and steel. So composites can really contribute to that. So all in all, we developed a concept which shows the flexibility of the material, but also the idea was that with this concept, Jones Manville can react very quickly together with partners on specific OEM RFIs. So it's more like a battery enclosure design toolbox, which can get adapted to different projects. And this is what we're really very proud on the result. And now Dana will summarize.
Yeah, so as Georg said, we work with others, and an example here is how we pulled in one compounder and a company that was very diligent about recommending solutions for sealing, for clips, and for the crushed honeycomb structure. So along the years, we learned who are the participants in the value chain, and we know who to ask for help and for partnering in terms of charting a full solution. One other partner was Engel. That's a large and very established equipment manufacturer leading in overmolding technology. So we went and asked them, is this concept doable at a level of, I think it was, 200,000 parts per year? So they said yes, and they recommended a process, and they said you can do that from one cell at the level that you are interested in. So we're trying to look at potential questions further on in the process and to analyze the concept holistically to see what it can bring. So we have continuous fiber reinforced thermoplastic, new organosheets. We have cost-effective materials. They're compatible with other thermoplastics. We really are able with these materials to deliver optimized crush performance through efficient use of packing space. We have the ability to play into the modular design space. But as we said earlier, that's not enough, so it's good to partner. It's good to be able to chart a full solution. In a nutshell, we have a concept that can compete with aluminum in terms of cost versus weight. Of course, if you add more carbon fiber to the design, the weight can be lower, the cost can be higher. But it's an attractive concept. It's attractive across various platforms, and it just shows that organosheets can be used in structural applications effectively. We are part of the solution. We are working with design and optimization partners, with process development, and really we believe that those kind of partnerships are key for developing full solutions. I do invite you to find us in the booth later on today or for the next 2 days. Georg will be available as well throughout the week. And then we'll be looking forward to talking to you more about new materials and what we're doing. And thank you again. I hope you have a nice GC.